Hello, so welcome for another MATH321 video. Here I'm going to cover false position, and the secant method. And we'll come back to, because they're related, and we'll come back to discuss the secant method when we talk about Newton-Raphson. Okay, so the basic idea with bisect is that, just graphically, we have two initial estimates around some root that we know, at least one, because we know that the function changes sign, and based on the intermediate value theorem, we assume that our function is continuous, which means there has to be at least one root, right? Then we chop it up. So basically we should be let's say x1 and y1. So let me just graphically represent that as two lines. Then we chop it up, right? We find a bit in between, and for this particular function that ends up being x2, and we take y2 to be this end as well. So we've chopped the domain up in half, and then we keep doing that. x3, that'll be y3. Chop it in half, and that'll end up being y4, and x3 will end up being equal to x4. So chop, 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 and you converge to whatever value that is. You don't need to know the value of the function. Think about it, right? You don't need to know the value of the function. Only need to know how to calculate a product, right? X sum I times whatever the midpoint is that you're calculating. So you only need to work out the sign of this. Now, I haven't come across this in the literature, but presumably there are shortcuts you might be able to take when calculating this, as opposed to calculating the individual values of the function. So you might be able to save a few additions or multiplications or something when you run the algorithm. In any case, linear convergence, and it's guaranteed to converge. Think about the conditions under which it is guaranteed to converge. Okay, so the false position works differently. Similar idea. It is also a bracketing method, so you have pairs of numbers between which you know that there's always a root. So start with an x1, and here we do care about the value. Start with an x2, and again here we do care about the value. So in the bisect method we say we want to get an approximation for where the root is, and that approximation is to find the midpoint. And sometimes the midpoint is a very good approximation, and sometimes the midpoint is a very bad approximation, just guaranteed to converge. False position says that instead of taking the midpoint, how about we draw the line between these 2 points and take this point as our estimate. Then exactly the same algorithm is used. So false position is exactly the same as bisect, except that linear interpolation is used to find the next best estimate. Right, then the same thing happens as with bisect. So then you check if x1 times xm is less than 0. If so, then you let x2 equal x1, and you let y2 equal m, just like with bisect, and you start off again. You run the algorithm again. Ugh. Throwing ink all over the place. I refilled it. I guess maybe I overfilled it or something. Okay. If x1 and xm is greater than 0, then of course x2 equals m and y2 equals y1. And if m happens to equal 0, then you're done. So, same as bisect in this regard. Okay. So I find the line in between. That gives me my new estimate. So here's our interval, and then we take our new estimate. We get that. Take a new estimate. And you see what's going on. We're approaching from one side here. This endpoint isn't altering very much because the function is concave, so the line will always be to its left and one-sided approach. So that's one of the main disadvantages, and you can see how this interval is decreasing slower than at half, or at least the way that I've drawn it is meant to imply that the interval is decreasing slower than a half. So can have one-sided approach. Meaning that yi ends up equal to something like y1 for all I, or at least when it settles down into whatever the concave region is. Convergence is very slow. Much slower than bisect. And there's ways to combat this, and I will talk about that in just a moment. Okay, so I haven't given you a formula yet for this. So straight line between 2 points, and those 2 points are x2, fx2, and x1, fx1. So the equation for the line between them. And this is equal to 0. So the sum x, or sum m, we want to find m, where this is equal to 0. And if you rearrange this, you get m is equal to x1 minus f of x1 times x2 minus x1 over fx2 minus fx1. Okay. Now, subtractions here for numbers that could be very small or of similar orders, so there could be large amounts of error here and here. Yeah. So it's a good idea to rearrange this, and if you do that, you get fx1, fx2 minus x2, fx1 divided by fx2 minus fx1. And this is an excellent form, because it turns out that this is really an addition, and the same goes for the top. Well, for the top it requires that x1 and x2 are both greater than 0, or x1, x2 are both less than 0. But that's usually the case, unless you have a 0 specifically at 0, which you could check for explicitly in the algorithm if you really wanted to. So with additions on top and bottom, this is pretty good. There's a nice symmetry to this, which some people think is very nice. I've seen claims that the symmetry is good for numerical, helps for numerical stability in this particular equation, though I haven't seen any proof of that, and I haven't seen anything beyond claims, so I don't know. But in any case, this is slightly better than that for the reasons I stated, because we're doing addition and division rather than subtractions. Sorry, my pen's being a bit weird here. There we go, that's better. So that's false position. And because we know that the root is always between, so by design, and hopefully you can see this is true. If you can't, you need to convince yourself, write out a proof for it. By design, the 0 is always in the xi, yi, which means that you have some advantages. What do I mean by that? Even if you have error in these two numbers, you know that the root is between them, and that error presumably can't affect that too much. So the number x won't be exact, the number y won't be exact, but you know that the function has a sign there and is non-zero, so it's good for control. And as the algorithm progresses, you can use this to work out where the 0 is. You'll see in a moment with the second method what goes wrong where you don't root bracket. The issue is that the elements of the sequence that's converging to the root could have a very small distance between them, implying that convergence is happening quite rapidly, but there's no guarantee that it is. And importantly, you don't know where the 0 is, which means that you don't know whether that small distance between elements in the sequence that's converging is telling you information that you can interpret appropriately. Whereas here, you always know how far away really you are from the root, because you can take the difference between these things and you know the root is always in between. So there's some extra information in bracketing methods, which is good. Okay, so we saw before that for concave functions, you're always going to approach the root from one side. So I'm going to call that one-sided approach, which means that one of the edges of your interval will never change. So this ends up being yi for all I. That's an issue, right? Because it means that instead of converging to a point, you're converging to an interval. That interval being the root and yi. By convergence to a point, I mean that the xi's all converge to the, I should say 0, sorry, converge to the 0, and the yi's converge to the 0. So this is a big problem, and you can do lots of things to it. There are lots of things to fix it. One algorithm that I've seen is that if the difference between yi and xi is very close to the previous distance between yi and xi, then instead of assuming one-sided convergence in this way, instead of working with the points xi, fxi, and yi, fyi, work with the points xi, fxi, and yi, fyi divided by 2. So this means that when you have this going on, here's your yi, fyi, and you have one-sided convergence, So let's say you have two iterations of one-sided convergence. You see that the difference between the intervals is very small, so there's probably some error happening. Instead of using this point, pick this point here. In order to try and break away to get a line that's to the right of the concave portion. And of course you could do the division by 2 multiple times. Remember, in the bisect method we didn't care what the value of the function was, we only cared that it had the correct sign. Here we're maintaining the sign. It's not actually important for the false position what the value of the function is. What matters is that it has the same sign, that the value that we have associated with yi and the value that we have associated with the xi has the same sign as the function itself, and then the root will be found using the bracketing method by slowly converging in. You could put anything in here. You could even intersperse the false position with the bisection method. Say you have this happening where the distance between the two intervals is very small. So this is very close. You could do a couple of steps of bisection instead. So this approach here is sometimes referred to as modified false position. But you could use bisection instead. And that's because the function value doesn't matter. It only matters that the signs associated to the ends of the brackets are appropriate. So that's false position. Error convergence, for the rate of convergence for false position is difficult to calculate. So I'm not going to do it. Okay. Instead, I'm going to show you the second method. And I will work out the convergence for the second method, and that will have an implication for the convergence for the false position. So secant is almost exactly the same as false position. We have x1, and I'm not going to call this y1, I'm going to call it x2. We use a straight line, find the intersection, and I'll pick that as x3. Then I use x2 and x3 to find another estimate, and I'm going to call that x4. Then I use x3 and x4 to find another estimate, and I will call that x5. So this is not bracketing, meaning that we don't know where the root is. This was a secant starting with a bracketed root. You could also start without a bracketed root. There's x1, there's x2, draw a line between them, there's my x3, there's my x4, so on and so forth. Right, because we're using the line to estimate where the next position of the root is, we get linear interpolation of the function. So the line that I'm drawing here is basically the algorithm trying to guess where the function goes through the x-axis. So it's assuming that the function is a straight line, which is not necessarily true, but anyway, linear interpolation of the function to get the next best estimate. Oops. So how does this work? Same formula as before. So given xi and xi minus 1, the next estimate, sorry, misspelt, is xi plus 1, which is excuse me, I'm just looking through my notes. and I'll use the symmetrized one, equation x I minus 1 fxi minus xi fxi minus 1 divided by fx2 minus I fxi plus 1. All the same benefits that apply to false position apply to this. So we get a sequence. And essentially, the sequence must converge to the 0. We have to prove that, of course. Okay. Right. So let f from the real numbers to the real numbers be I think we need second C2, and let's assume that it's C2 on some, I think we need to require that it's C2 on some interval, and we need to know that there's a 0 in the interval, right? So we need to know that FA times FB is less than 0. Okay, now some notation. Define FAB to equal to FB minus FA over B minus A, and FABC to be equal to FAB minus FBC over AC. And these are examples of something called divided difference notation. Right, now we know that xk plus 1, xk, and here I'm using the full form of, well, the unsymmetrized version of the equations because it's convenient for me. And we're not going to plug these into a calculator. I'm just doing the into a computer. I'm just doing the calculation this way to determine the error. Okay. Now let alpha of a b be such that f of alpha equals 0. Then we know that alpha minus xk plus I, which will end up being the error, of course, or is the error, alpha minus xk, which is the previous error, plus this term here, which you can rewrite as, and you need to prove this, f xk minus 1 xk minus f xk the root alpha divided by f xk minus 1 xk. Now this can be rewritten as alpha minus xk times alpha minus xk minus 1 minus the function xk minus 1 xk alpha divided by f xk minus 1 xk. Right, current error, previous error, and the error before that, and this thing. So what is this thing? Now I claim that, and again, this is the sort of thing that you should have a look through yourself and prove yourself. So the intermediate value theorem, implies that let's say we have f of intermediate value theorem? No, the mean value theorem. Mean value theorem. Hold on a second. I think I've written it down wrong. Right, mean value theorem. So think about this. F xk minus 1 xk is equal to f of xk minus f of xk minus 1 divided by xk minus 1. We don't know that xk is actually bigger than xk minus 1, but whatever. So f has been assumed to be C2 over this interval AB. So as long as xk and xk minus 1 are in this interval, the mean value theorem applies, and there exists some value, which I'm going to denote by zeta, in, well, the interval is a little awkward to specify because I don't know whether xk is bigger than or less than xk minus 1. So there exists a zeta in the minimum of xk and xk minus 1 to the maximum of xk minus 1. So that f xk minus 1 xk is equal to f dash of zeta. And I claim the following. I'm going to leave this for you to do in an assignment or a tutorial, so make sure you know how to do this. I claim that the mean value theorem implies that, here we go, there exists, I'm going to say eta in the interval, the minimum of xk minus 1, xk and alpha, and the maximum of xk minus 1, xk and alpha, so that the divided difference xk minus 1, xk and alpha is equal to 1/2 of the second derivative of our function eta. So this allows us to conclude that alpha minus xk plus 1 is equal to alpha minus xk alpha minus xk minus 1 times a number. Okay, so this is what we want is, so if there exists m greater than or equal to for all eta and zeta, an element of AB. And the problem here is, of course, if the derivative of the function, the second derivative of the function becomes 0. If the second derivative of the function is 0, the function itself is linear, and false position will find the root in one iteration, or secant will find the root in one iteration, because the linear interpolation of the function will be exact. So you're allowed to assume that this thing is not 0, because you can prove that if it is 0, the convergence will be much better than if it wasn't. So assuming that this isn't 0, then this bound will exist because our function is C2. So let me rephrase it. If dash dash z equals 0, convergence will be much better. Since the linear approximation will be, it won't be exact, but it'll be closer. And in fact, the closer the points xk and xk minus 1 get to each other, the better the linear approximation will be. So convergence will even accelerate as you repeat. So this is a very nice outcome if you have this. I guess you could probably prove that convergence is third order. In any case, it's very good. Be close. So so if we assume it's not equal 0 on for zeta I've written z in AB, then continuity over the compact interval guarantees the existence of M. And with more work, you can show what happens. I'm going to ignore this case. Maybe we should come back to it in a tutorial if someone is interested enough. It's probably worthwhile. Okay, so in this case, I'm now going to let epsilon k, the error of the kth approximation, be equal to the root minus xk. And now the equation that we have is ek plus 1 equals ek times ek minus 1 times some constant less than or equal to. Okay, so now the argument gets a little vaguer, and yeah, the argument gets a little vaguer, and for that I apologize, but you'll see how it works. So let's times everything by m. This is a recurrence relation, so let e k equal m epsilon k. So we have a recurrence relation, ek plus 1 is always less than or equal to ek times ek minus 1. So if you let delta equal the maximum error in the first two approximates, then we can see that E2 is less than or equal to E0 times E1, which is delta 2. Less than or equal to delta 2. E3, which is less than or equal to E2 times E1. E2 was delta 2, E1 was delta, so that's delta 3. E4 is less than or equal to E3 times E2. E3 is less than or equal to delta 3, E2 is less than or equal to delta 2, so this is delta 5. You can see that each step the exponent is increasing. It's the sum of the previous two. This implies that Ek is less than or equal to delta Fk, where Fk is the kth Fibonacci number. Right, now it is possible to write the Fk, the kth Fibonacci number like this. Fk is equal to 1 over the square root of 5, and this is where r plus or minus is equal to 1 plus or minus the square root of 5 over 2. Now, since r minus of k goes to 0 as k goes to infinity, f of k tends to r plus k plus 1 over the square root of 5, which is 1 over the square root of 5 times rk plus r plus an extra 1. So ek, which is less than or equal to delta fk, which is less than or equal to, for large k, well, it's always going to be less than because this term here is negative, but for large k this will be a better approximate. delta to the power of 1 square root of 5 r plus k times r plus. And here's the interesting bit. This is equal to delta 1 over square root of 5 rk plus times delta plus. Right, and this is our bound for, we know that this is ek minus 1. So the error bound is increasing by r plus each iteration. And while what I've shown does not explicitly fit the definition of error convergence that I showed you, people take this to mean that the error convergence of the secant method is r plus 1 plus square root of 5 over 2, which is the golden ratio. Right, so now, talking about orders of convergence. Generally, bisect is linear, and that is going to be generally slower than, except for pathological examples, than false position. And the argument here is that because false position uses information about the value of the function, to get a better approximate of the zero. And this is generally thought to be less than the secant method. And convergence here is, it's often called superlinear as well, because r plus is 1.6 something. And this is argued because false position sometimes uses old estimates in its linear approximation. Okay. So there is another way to view the convergence, which some people might like a bit better, but it still doesn't connect terribly well with the definition I showed you. But in any case, so we have ek plus 1, or C convergence like this. Is less than or equal to ek minus 1. Assume worst performance. Then we have ek plus 1 is equal to ek times ek minus 1. Alright, this means we have log of ek plus 1 is equal to log of ek plus log of ek minus 1. This is a recurrence relation, and its solutions can be shown to satisfy a certain property. Recurrence equation. are such that the limit as k goes to infinity of the log of ek plus 1 minus r plus of log of ek equals 0. So this is equivalent to implying that as the limit as k goes to infinity of log of ek plus 1 divided by ek r plus equals 0. So for large k, there exists ck so that ek plus 1 is less than or equal to ck ek r plus. Dependence here is needed because, well, I haven't proven that there is some fixed constant, or even that there's an upper bound to the constant. But anyway, so again, this fits a little better with the definition of error occurrence I showed you before, and shows that the order of convergence is the golden ratio. Either way is fine. Both estimates involve issues taking limits, and as a consequence, this only holds for large k. Right, so that's false position and the second method.